In this video, we are going to be doing Chapter 11, number 34. A puck of mass 80 grams and radius 4 centimeters slides along an air table at a speed of 1.5 meters per second, as shown in the figure. So, here is our puck. And makes a glancing collision with a second puck of radius 6 centimeters and mass 120 grams, initially at rest, such that their rims just touch. Because the rims are coated with instant-acting glue, the pucks stick together and spin after the collision. A. What is the angular momentum of the system relative to the center of mass? B. What is the angular speed about the center of mass? So, first we have to recognize that this is a conservation of angular momentum problem. So, the momentum in the before scenario is going to equal the momentum in the after scenario. So, Part A is actually pretty easy to answer. We just have to find what the angular momentum of puck 1 is relative to the center of mass. So the axis of rotation is through the center of mass. Step number 1 is to find what the center of mass is. So I have this here for you. I'm calling the origin right here. 0.04 meters would be the center of puck 1. 0.08 meters is the diameter of puck 1. And then from the origin, the middle of puck 2 would be at 0.14 meters because it has a radius of 6 centimeters. So the center of mass is going to be the mass of the first puck times the location of its center of mass, plus the mass of the second puck times the location of its center of mass, divided by the masses added together. So the mass of the first puck is 0.08 kilograms, that would be 80 grams from the previous slide, and the location of its center of mass is 0.04. The mass of the second puck is 120 grams, so 0.12 kilograms, and its center of mass is located at 0.14, as you can see in the diagram. So we get that the center of mass is at 0.1 meters compared to the origin, so that would be around here at this point. Now that we've found the center of mass, we just need to find the angular momentum of puck 1. So the center of mass of puck 1 is, let me get my pen up here. The center of mass of puck 1 is this red distance, give me just a second, I did that incorrectly. The center of mass of puck 1 is about this distance away from the center of mass being about right here. So the center of mass of puck 1 is at 0.04, so we can say that it is 0.1 minus 0.04 equals 0.06 meters from the axis of rotation. And we know that our formula for angular momentum is L equals mvr. In this case, m is 0.08, v is 1.5, and r is 0.06. So we get that the angular momentum is equal to 0.0072 kilograms times meter squared per second. So this, because momentum is conserved, is our answer to part A. Now, part B asks us to find the angular speed of the system after the pucks stick together. So there we need to further use conservation of angular momentum. We need to find the final moment of inertia of the system of both pucks. To do this, we will model the pucks as solid disks and use the parallel axis theorem. So for puck number 1, well, just remember that the moment of inertia for a disk is 1/2 mr squared. And then we need to use the parallel axis theorem So this is where the parallel axis theorem comes into play. D1 is the distance from the axis of rotation, which we already figured out in part A of the problem. So we just plug in our numbers, and we get that the moment of inertia for disk 1 is this number right here, 3.52 times 10 to the negative fourth. For disk 2, it's going to be the same formula, except it's M2, R2, and D2, etc. So for the second puck, I just want to point out that the distance from the axis of rotation is 0.14 minus 0.1, so that's where the 0.04 comes in. If you plug all those numbers into your calculator, you get 4.08 times 10 to the negative fourth. So the total moment of inertia of the system of pucks, so IF equals I1 plus I2, is 7.6 times 10 to the negative fourth. Now that we've found our moment of inertia, we can plug it into the conservation of angular momentum. So this number right here is what we calculated for part A. We know that is representative of the initial angular momentum of the system. And this right here is the final moment of inertia times the final angular speed. So if we just plug in the moment of inertia we got on the previous slide, you can just solve for omega f, and you get that omega f equals 9.47 radians per second. And that is our final answer.